Okay, so this is a quick bit of revision for the exponential logarithmic and functions and trigonometrical functions and the chain rule, which on top of your knowledge about differentiating polynomials actually gives you ability to do some quite complicated differentiation. So let me go in and share my screen. So we go straight into this. So essentially, yeah, we basically have learned about differentiating terms like where n can be any number, fractional, negative fractional, whatever. And is the coefficient. And the power rule applies to all those cases, whatever n is and whatever a is. So it's very powerful. But what happens if we want to differentiate something like the power rule will not work in these situations. So we need something different. Now, in order to unpick this, what we need to do is we need to look at this particular function, a very important function. So this is a graph of y equals e to the power of x. Now this, what is e? Well, e is a constant which has got approximately the value 2.718. It's actually an irrational number, so the decimals actually go on forever. But it has this particular shape, and you can see it's always positive because e is always positive. So whatever power we raise it to is going to be positive. E to the power of 0. So when x is 0, it's actually the value of that is 1, and then of course it rises, exponentially, essentially. So that's what it looks like, but it has a very interesting property, does this, because this particular curve, the value of the gradient at any point is equal to the value of the function. So here at this point, the value of the function, well, x is 2, so the value of the function is e to the power of 2. We can work that out, 2.718 to the power of 2. What's it going to be? Something like 8 or something like that. Yeah, in fact, it's just short of 8, isn't it? But if we took the gradient there, in other words, we could draw the tangent and then measure its rise over its run, we would actually find that the gradient has that same value of, well, nearly 8, which is e squared to the power of 2, and so on, all the way along the curve, even for these negative values that, the value of the gradient there would be e to the power of -2, quite a low number because it's a very shallow gradient. So this is very useful in maths, and so if we have y equals e to the power of x, then what that's telling us is dy dx equals also e to the power of x. Really very, very powerful, very useful. Now, what we need to know is the inverse function of this as well. So if this function is to exponentiate it, we take a number and then we're exponentiating it by applying it as a power to the constant e, then what would be the inverse function? Well, the inverse function is this thing here called the natural log of x. Without going into too much detail about log base e and stuff like that, let's just have a look at this. Well, we can see, let me just scroll a little bit, that it's asymptotes. It never actually reaches the y-axis, just gets closer and closer to it. And when x is 1, then the log function is 0. A bit more space. So, so in other words, we would just write ln of 1 equals 0. And then as x increases, then you can see the gradient gets flatter and flatter. So this is the reverse function. Now, which is normally called an inverse function, but I like to call it the reverse function. So very much like our way of thinking, if we got f minus 1 of f of x, well, by definition, one of the, this is taken as one way and then the other's taken as the other way. F of x will take us from x to some value, and then f minus 1 will take us from some value back to x. So, that is the case. So, so equally, if we put these two things together, then what we get is, we can either look at it this way. Okay, we've got the reverse and the forward, or the forward and the reverse, and also, yeah. So in both these cases, we're going backwards and forwards. So it's just a question of where you start. If this is your number machine, you put an x in there, you get f of x out, and if you put f of x in there into this number machine, which is f minus 1, then you're going to get x out. So yeah, it doesn't matter whether we start there and go there and then back this way, or that way and round and back this way. It's the same idea. Now the other thing about this is we see that actually when x is very small, it's the gradient is going to be very high, and as we proceed, it gets flatter and flatter and flatter. And in derivative terms, if we have this function and then got dy dx, actually turns out, and we could derive this, but we'll just take that for granted. So we've got two important rules here, is that if y equals e to the power of x, then dy dx equals e to the power of x, and if y equals log n of x, then dy dx equals 1 over x. Okay, so important results there. So to remember those. The other thing is these basic trigonometrical equations. So this is the graph of sine x. And this is plotted, we always use radians. A radian is, there are 2 pi radians in a circle, which is obviously 360 degrees. 2 pi radians equals 360 degrees. Now, if you thought that you could only have sines up to 90 degrees, well, that's not the case. Again, not particularly for this video, but we can go right round the circle. We can carry on going around it and round as many times as we like, or we can go in reverse direction and we can have negative radians. And what we end up with is the sine wave. And I'm sure you will have heard of the sine wave. It's in everyday parlance. So this is sine of 0, which is 0. This here is pi by 2. That looks about it, doesn't it? 1 pi by 2. That's about 1.55, isn't it? So it's around about here. And this, the value is 1 here. Back to sine of pi, which is 0. Sine of 3 pi by 2, which is minus 1. And then back to this point here, to 2 pi, which is the same as sine of 0, which is 0. And if we're to look at the gradients at these key points, then at this point here, if we work this out, we'd actually find out the gradient is actually 1. the scales, the y scale and the x scale are different, so it's not obvious from there, but that is 1. When we look at this point here, the gradient of the turning point, so it's 0. At sine pi, it's -1. At sine 3 pi over 2, it's 0 again, and back to sine of 2 pi, and it is, therefore, it is 1 again. So that's how that is, and now this second one is a cosine of x. So it looks very similar, but it's but shifted, and we've got similar values. We've got 1 there, we've got 0 there. This is cosine of pi. We've got -1, 0, and back to 1. But the interesting thing now is if we look at the gradients of the sine x curve and compare them to the cosine values, the gradients of the sine to the values of the cosine, we find out that they are the same. And so, and therefore, we can express this in this particular way. So this is y equals sine x, and the gradients are given by the cosine curve. Not only that, but if we do it the other way around, we actually find that if we have that situation, y equals cosine of x, then the gradients are given as the negative of the value of the sine at that corresponding point. Again, not to worry too much about the derivation of all that, but again, a couple of rules to remember, because these are going to support doing some sort of fairly complicated stuff, differentiation. Right. Okay. So that's all good. Scribble that out. The chain rule. Okay. Now, one thing with derivatives that is not perhaps obvious, but is this the underlying rule behind the chain rule. So where we have, let's just write it out. So u would be a function of x, y a function of u, and we can essentially write this, because these are actually they're infinitesimally small concepts, but they are still valid ratios between each other. So we can actually do this and do this cancellation between the du's. So this is strangely a valid thing to do. So if we have an example like y equals sine of x plus e to the power of x, well, we can differentiate this bit, x plus e to the power of x, because this is polynomial, very simple. This is e to the power of x is the exponential, which we've just seen. So we can differentiate that. We can differentiate sine x as well, because we've seen how to do that. So that's sine x differentiates to cos x. But how do we do this? Well, what essentially we've got here is a composite function. This is, very much our g of f of x, where the f of x is x plus e to the power of x, and the g is the sine. Now, the sort of general rule is what we do is we differentiate the f, and then we multiply it by the derivative of the outer, the g, with respect to the inside. So that would simply give us the derivative of the f would be 1 plus e to the power of x. and the derivative of the g would, with respect to f, would be cosine of x plus e to the power of x. Now, that's a nice, easy way of remembering it, I think, but it was quite useful also because sometimes things are a bit more complicated, and it's quite useful to actually go through the substitution from first principles. So in this example here, if we were to let u equal x plus e to the power of x, then what we would have is du dx equals 1 plus e to the power of x. Okay. So our equation now becomes y equals sine u. So if we've got sine, y equals sine u, then dy du equals cos u, as we've seen. And also dy dx equals dy equals dy du times du dx. Okay, so dy du, we've just seen here, is cos u times du dx, which we've got up here, which is 1 plus e to the power of x. Now, once we substitute back in our u, which we wrote up here, then we end up with cos x plus e to the power of x times 1 plus e to the power of x. And that is really doing the chain rule by substitution. So we can use substitution if we wish. In many situations, we'll probably just be able to think it through and go, yeah, okay, this is my f, that times the derivative of g with respect to f, and work it that way. But there are more complicated examples where, to be honest, it's almost better to look at it and actually do a substitution. And in some situations, we might actually do a double substitution. So we get dy dx is going to be equal to dy du times du dv times dv dx. But more of that later. So it's useful to know anyway about the substitution mechanism, and you may use that if you wish, or just fall back on your other rule of multiplying the f by the derivative of f by the derivative of g with respect to f. And you know, either of those will get you the answer. Okay, so I hope that's been useful, and I'll see you in the next video.